At service now, let us look at it. Service now, how much will be the moment? I need to include service. At service stage, both live load and dead load will be acting. Now, C has further moved away from your T. How much it would have moved up? That is lever arm, and the lever arm is proportional to moment acting in the section divided by C. Now, what will be C? C will be now equal to effective pre-stressing force, which is 0.85 times P naught. Okay, that is what we are using here, and I am converting into Newton, so I multiply it by 1000. So, if you substitute, lever arm is 540.23. Now, what is EC? EC is nothing but EZ minus E. So, that is what we are going to use. So, which is 140.23 millimeters. So, EC, if it is a positive value, it is going to be above CGC. So, we can say that the pressure line is going to be above CGC. Magnitude of EC is lesser than KT, so there is not going to be tension. So, at service, it is not going to create any tension at the bottom, but however, at transfer, it is going to create some tension. So, if you plot the location of your pressure line, this is again at mid span, okay, where the maximum moments are acting, right. So, this is your CGC, and you find this is your Kern zone, but this is a Kern zone, which is, what is the Kern zone? This is 243.4 or something, right, 243.4, right. But however, here you see here, this is your EC at transfer, this is at transfer. Right. Now, when you look at it, at top it is going to be at 140, this is at service. So, this is EC. Okay. So, you see here the pressure line at transfer is getting violated, it is going below the Kern zone, which is not good, but however, at service still it is within the top Kern point. So, this is the way we can do it. Now, how do we calculate the stresses in the cross section? That is also very straightforward. The stresses can be written in a generic form like this, but of course, it is negative or compression, it depends upon which location you are doing the calculation. It will be always the first point, concentric effect is minus P by A. The next point is P into E is the moment due to pre-stress, and Y will be either top or bottom, wherever you are doing calculation. Depending upon that, it will be negative or compression. Negative means compression, positive means tension. Similarly, due to external loads. So, now let us look at, this is a concentric effect, this is a pre-stressing effect, this is due to pre-stressing moment, this is concentric pre-stress, and this is due to external loads. Okay, then you get your net percentages. P naught by A is 8.62 megapascal. Now, let us look at stress at the top fiber is this, which is 14.16 megapascal, and the dead load, because at transfer we are going to have only dead load moment. So, that is the reason 348 only we are taking, and that is at the top it is going to create compression, which is negative 4.92 megapascal. So, net effect at transfer, when you look at it, this is concentric effect, which is minus P naught by A, and this is your pre-stressing moment, this is your MP, okay, and this is your load MDL effect, okay, this gives this, right. And the net effect, if you see, I am getting stress of 0.62 megapascal, which is tension, but it is much lesser than your FCR, so there is no problem. Now, stress at the bottom, when you look at it again, here it is going to be pre-stressing force is going to create compression, again it is going to be minus 14.16, but the load is going to create plus, which is plus 4.92, and I add all of them, net it is still in compression of negative 17.86. Okay, so now how about calculation of stresses at service? Now, PE by A is 0.85 times P by A, which is 7.32 megapascal. Now, why are we doing at service? Service, I am going to have some losses will be there. So, P naught becomes PE, and that is equal to 0.85 P naught, 15%, I am assuming that 15% losses, right. So, that is the reason I am taking 0.85, and the concentric stress is going to be 7.32. Similarly, pre-stressing moment is going to give 12 and live load moment is going to give 11.33, dead load moment is going to give 4.92. So, if you add all of them, stress at the top now is going to be in compression, okay, because the live load is creating lot of compression. So, the previous tension has been converted into compression. Now, stress at the bottom fiber, again do the same thing and you get pre-stressing force moment of negative 12 megapascal, live load moment of 11.33, dead load moment of 4.92. When you add all of them, I get negative 3 megapascal compression. So, at service when you look at it, both top and bottom I have stress of compression, right. So, if you plot it, this is the way it is going to look like, right. So, I am going to get, okay, maybe I think, let me see, I think there is a small mistake in here, let me see. So, if you go back, yeah, this is, this is 513. So, this is plus, so this is in tension, right, at transfer. So, if you go back to the curve, that means this has to be, this is not correct, this is plus, right. So, it should go like this, small value, very, very small value, and it is going to go like this. Okay, so, this is not correct and this is plus and this is minus. The entire section is pretty much in compression, but only small tension has developed. Okay. For type, it is not strictly a type 1, so that means violating the type 1, but however in service you see here everything is in compression, this is negative, this is also negative, everything is in compression. Now, our allowable stresses, if you see, negative 25 and 2.5, so the stresses are within the allowable limits, no problem at all, right. So, here we are allowing tension of 2.5 megapascal, so plus 6.2 at service, sorry, at transfer is not really a big concern. Okay. Now, let us quickly calculate what are the deflections at midspan. Okay. So, now deflections calculations, you know the moment of inertia, length is given to you, and P naught is the pre-stressing force is given to you as 2500 kilonewton, E is 400, load is 6.96 kilonewton per meter. Now, deflection due to pre-stressing force, let us look at it again from Moore's theorem, right. So, it is A is your deflection, the moment area of the moment diagram divided by EI. So, and you take the moment of that. So, if you substitute that for this particular case, which is 5 by 48 EI into PEL square, and A is equal to 5000 square root of FCK, and you find that as deflection is going to be 37.32 millimeter, which is upward. Due to self weight of the beam, it is going to be 5 by 384 EI into WL power 4, right, and this is deflection due to uniformly distributed load, and you get force of deflection of 12.98 millimeter downwards. So, if you see here, the net deflection is going to be negative 37.32 plus 12.98, I am getting 24.34 upwards, and see that, you know, still that this deflection even at self weight, it is still, it is upward, right. So, we have put lot of pre-stress, but when you have live load coming, then everything will come down to 0. This is only final deflection due to pre-stress and self weight. Now, we can also look at this. So, let us summarize what we have discussed. Today, we have explained the concept of Kern points, pressure line, cracking moment using Kern points, and we also learnt about camber, deflections and stresses, how to do the stress analysis for a flexural member, right. So, with that we are completing this part 4 of this module 4. We will continue the other parts in the next lecture. Thank you.